So how do we find the equation of this best fit line? In Python, we will be using the ordinary least squares, or OLS, function from the stats model formula API library. Here is the general code that we would use to estimate the regression equation. This code might look familiar to you because we use the same smf.ols function to test an analysis of variance in Course 2 Data Analysis Tools. First, I name the object that will be produced by the OLS function. Then an equal sign followed by the function smf.ols from the stats model formula API library. Then, within parentheses, I write my formula including the name of my quantitative response variable, which is called quant_response in the model, followed by a tilde and the name of my quantitative explanatory variable, quant_explanatory. Note that my entire formula is enclosed within quotation marks. I add a comma, then type data equals and the name of my data frame. Outside the parentheses, I type .fit, followed by an open and closed parenthesis to request fit statistics for the model I have just defined. Then, as always, I need to ask Python to print the fit statistics for my model using the print function and in parentheses the name of my object, .summary, and then open and close parentheses. For this sample research question from the Gapminder dataset, we first import the libraries we will need: NumPy, Pandas, Stats Model API as SM, and the Stats Model Formula API as SMF. Note that we are giving the Stats Model API library the abbreviated name SM, and the Stats Model Formula API library the abbreviated name SMF. These are the names that we will use to refer to these libraries later on in the Python script. Then, we call in the Gapminder dataset using the read.csv function and make sure that we convert the variable types to numeric with the pandas to numeric function. We use the print function to have Python print the title OLS regression model for the association between urban rate and internet use rate as part of the output that will be displayed in the IPython console in the lower right-hand corner of the screen. We give the object that will be produced by the OLS function the name reg1, followed by an equal sign. After the equal sign, we include smf.ols. Within parentheses, I then write my formula, the name of my quantitative response variable, internet use rate, followed by a tilde and the name of my quantitative explanatory variable, urban rate. Note again that the entire formula is in quotes. I add a comma after the formula in quotes, then the name of the data frame I'm working with, which is called data. Finally, I ask Python to print the results from my model reg1. Let's run this program and look at the output in the IPython console. Depth variable shows us the name of the response variable. no.observations shows us the number of observations that had valid data on both the response and explanatory variables and were therefore included in the analysis. The F statistic is 113.7, and the p-value is very small, considerably less than our alpha level of 0.05, which tells us that we can reject the null hypothesis and conclude that urban rate is significantly associated with internet use rate. Next, let's move to the parameter estimates, which are in the COEF column. Here, we have the estimates, also known as coefficients or beta weights, for both our intercept and for the variable urban rate. Thus, the coefficient for urban rate is 0.72, and the intercept is negative 4.90. So now we know that our equation for the best fit line of this graph is internet use rate equals minus 4.90 plus 0.72 times urban rate. Before we analyze this equation a little more in depth, let's look at some more components of our output. For example, looking just at the output for the coefficients, we have a column labeled p greater than the absolute value of t, which gives us the p-value for our explanatory variables association with the response variable. This p-value will be the same one we get if we run a Pearson correlation on these two variables. The p-value is 0.000, which means that it's really small. Here you would report the p-value as p less than 0.0001. The OLS function also gives an R-square value, a value that we talked about in Course 2, Data Analysis Tools, in the module on Pearson correlation. It is the proportion of the variance in the response variable that can be explained by the explanatory variable. We now know that this model accounts for about 38% of the variability we see in our response variable, internet use rate.
Look at how our equation is written. Y is a function of the variable x and some constant. Thus, as x changes, y will change with it. In building this model, we're saying that we believe that x relates to y in some meaningful way. What's exciting about this equation is that we can also use it to generate predicted values for y. The symbol that we use for predicted values of y is y hat. For example, let's say we're told that a country has 80% urbanization. Can we predict their level of internet use? Yes. We just plug the value 80 into our equation where we have our x value. As you can see, in a country with 80% urbanization, we would expect 52.7 people out of every 100 to use the internet. Also note from our beta sub 1 that this value is by how much internet use would increase for every 1 unit increase in urban rate. For example, if we had a country with 81% urbanization, we would know that we would expect their internet use rate to be 0.72 people higher, that is almost 1 person, than a country with 80% urbanization. However, note that this is only the expected internet use rate given what we know about urbanization. It's the value that rests exactly on the best fit line. Unless our data were perfectly correlated, we would anticipate that our expected value and our observed values would differ from one another to some extent. From our analysis, we now know that there's a statistically significant association between urban rate and internet use rate, and we can also tell you what we would expect internet use rate to be for a given country given its urban rate. This statistical model has opened the doors to being able to better understand what's really going on between internet use rate and urbanization. As long as we keep in mind that we're limited by the fact that we impose the causal model rather than being able to directly test for causation, and that expected data is not the same as observed data, we're still able to explain much about this relationship of interest.
For example, Canada has an urban rate of about 80%. However, its internet use rate is observed at 81.3, not 52.7. This is exactly why we include an error term in our model. We are not perfect diviners of the future. What we can do with statistics, however, is identify trends in our data and use those trends to look at what we would expect our data to look like. These trends are incredibly important.